Thank you, everyone, for joining us today. My name is John Goss. I'm former president of the Astronomical League. This is all in recognition of the 75th anniversary of the League, which takes place on November 15th later on this year. Today, our talk is being presented by Carl Hergenrother, who will be speaking about the OSIRIS-REX mission. It's an asteroid sample return mission from the asteroid Bennu, which will return later on in the next couple of years. Carl is currently a software developer for upcoming missions, and he has been involved quite a bit with the OSIRIS-REX, and he will talk to us today about this interesting mission, something quite unique, bringing back a sample of another asteroid to Earth. So Carl, would you like to take over right now and tell us all about this fascinating topic?
Thank you, John. Yeah, so what I'm going to be talking about today is the OSIRIS-REX mission, which is a NASA-funded spacecraft to go to the Near-Earth Asteroid Bennu. In fact, it's already gone to the Near-Earth Asteroid Bennu. Collect a sample from its surface and bring that sample back to Earth for analysis. So what is OSIRIS-REX? Well, just based by the name, you know it's an acronym. Back in the old days, if this were the 1960s and 70s, the mission probably would have been called New Frontiers 3 because it was the third mission in the NASA's New Frontiers category of spacecraft. But a lot of missions these days have acronyms. And for OSIRIS-REX, the acronym actually spells out the various research goals of the mission. It's looking at origins. In particular, where did the water and organics that are on Earth, that in fact are in our bodies, where did those come from? Did they come from asteroids like Bennu, which is a carbonaceous asteroid, which means carbon rich? Spectral interpretation. We've got almost 1 million asteroids that we know of in the asteroid belt. There's hundreds of thousands of meteorites on Earth. And yet, when you look at the spectral information, photometric information of meteorites, compare them to asteroids, there usually isn't a one-to-one match. So by going to an asteroid, observing it up close, and even bringing material back, possibly material that we already have in our collection or similar material in our collection, we can have a better understanding of, okay, what does this meteorite actually tell us about the asteroids that are out there? Resource identification. At some point in the future, human beings will be living out among the asteroids and the planets kind of in interplanetary space. And so we're going to have to learn to live with the resources that are out there. And asteroids, carbonaceous asteroids like Bennu, which are carbon rich, which are water rich, actually will probably serve as kind of the gas stations of the future. So by, again, going to a carbonaceous object, bringing samples back, we can learn a little more about how we could actually live off the resources that are out there. Security. We did not know this when we actually selected Bennu as our target, almost 15 years ago. But Bennu is listed as one of the most dangerous asteroids out there. Now, most dangerous is a relative term. It just means that there's a 1 in about 2,000 to 3,000 chance of Bennu hitting the Earth well after we're gone, but in about 150 to 200 years, there is that possibility. So by going to an asteroid like Bennu, studying it up close, not only are we refining its orbit, we're also able to collect data that would allow the models that we would use to, model its motion into the future and whether or not it would truly hit the Earth. We can refine those models by actually having real ground truth data by being near the asteroid. And Regolith Explorer. Regolith is kind of a fancy science word for dirt. It's the soil that you find on the surface of the asteroid, the pebbles, the fine particles. And this is a mission where we were able to get very high resolution imagery of a lot of the surface, as well as bring some of this material back. So it's the first mission where we really did a global survey down to even centimeter sized particles of the surface of this object. OSIRIS-REX is a PI-led mission. What PI means that the principal investigator leads it. So it's not a NASA field center necessarily, or it's a mission that didn't come out of a directive from Congress. It was one where they actually put up a competition and asked various academic and industry partners in the United States to come up with ideas for planetary missions. And OSIRIS-REX was our idea. And it's a collaboration between the University of Arizona, NASA Goddard Space Flight Center, and Lockheed Martin, who are the main partners. But we also had significant contributions from other organizations like Arizona State University, the Canadian Space Agency, the French Space Agency, CNES, Kinetics, which is a private company and did almost all of our navigation work. MIT and Harvard contributed an instrument. And of course, United Launch Alliance launched us on an Atlas V. So NASA has a bunch of spacecraft that are currently out there orbiting. And some of these are asteroid related. Of course, we have OSIRIS-REX. We also have NEO-WISE, which is discovering a lot of, especially dark asteroids right now. But in the future, we're going to have spacecraft like Lucy and Psyche and Janus also going out there to various asteroids. About 16 near-Earth and main belt asteroids have been visited by spacecraft already. And most of these encounters were just flybys, usually on their way to something else. The first asteroid flyby was 951 Gaspra back in 1991 by Galileo, as it was doing its various Earth gravity assists on its way to Jupiter. It was only the second flyby, which again was by Galileo, and this was of 243 Ida, that made the first major spacecraft asteroid discovery when it discovered a satellite in orbit around Ida. 5 asteroids have been orbited. Eros, which is a near-Earth object, was orbited by Near Shoemaker back in the late 90s, and eventually Near ended up landing on its surface. Ceres, which is the largest main belt asteroid, and Vesta, which is the brightest main belt asteroid, were both orbited by Dawn, and Dawn is still at Ceres right now. Itokawa, which was a small near-Earth asteroid, was orbited and had its sample collected by the Hayabusa spacecraft, which was a Japanese spacecraft. The Japanese also launched Hayabusa 2, which just came back a few months ago to Ryugu, which is almost, you can think of like a sibling asteroid to Bennu. It looks very similar, same basic type, a little bit larger. And of course, we have OSIRIS-REX at Bennu itself. So the spacecraft was equipped with a whole suite of instrumentation to study the asteroid from basically the equivalent of your B filter, you've got it in your backyard, your blue band filter, all the way out to 100 microns, which is well into the thermal infrared range. And we also had instruments that were looking at the X-ray wavelengths, looking for the signal of minerals that were being fluoresced by solar radiation impacting on the surface. For the imagers, we had actually about 6 different cameras, not counting the star trackers, which almost every spacecraft has. 6 imagers that were looking at the asteroid or looking around the asteroid. We had Polycam, which was you can think of as an 8-inch Ritchie Creighton, except it was much faster than your usual RC telescope. It was about f3, so it was pretty fast. And the reason why it's called Polycam is because it had 2 roles. One is it was effectively our light bucket. It's what we used to detect the asteroid when we were about 2 million kilometers away, and it was about 13th magnitude to first pick up the asteroid among the background stars. But also it has a focus mechanism, and not only could it focus at infinity, it could change its focus and still stay in focus when we were within 200 meters. And at that point, it became our high resolution imager and was able to get, centimeter scale resolution on the surface. We also had MapCam, which was more of a wide field. It was effectively, you can think of as a 125 millimeter f3 telephoto lens, covered about 4 degrees on the sky. And that one had, rather than a focus mechanism, it had a filter wheel. We did have 4 filters in there, which again, you can think of as your B filter, your V filter, and then there were 2 that were kind of in the R and I band that were more specifically selected because they were good for differentiating between different material on the surface of asteroids. And then StamCam, which was a really wide field imager, its sole job was only to image the sample collection as it was occurring. And we'll have some cool videos taken from StamCam later in the presentation. Almost all spacecraft that have to do some sort of maneuvering around an object. And of course, when you're orbiting or maneuvering around an object that's only a half kilometer across, you need a really wide field of view to ensure you actually get that object, because of your uncertainties, you can be way off from where you think you are. So we had 2 what we call nav cams. They were part of this TAGCAMS touch and go camera system. These 2 nav cams that were specifically meant to do navigation and find the asteroid so we can figure out where the spacecraft was. And they were never intended to be used for science, but, spoiler, a few slides ahead, we actually ended up using them for science when we made a quite unexpected discovery. And then we had one camera called STOCAM, and STOCAM really just looked at the sample return capsule to see how it was doing and to to monitor how we actually stowed the sample in the capsule and make sure everything worked out well. We had 2 infrared spectrometers, OVIRS and OTES. OVIRS actually covers the visual bands as well, out to 4.3 microns, so it gets kind of the thermal tail. And then OTES, which went all the way from where, a little bit past where OVIRS left off, all the way to 100 micron, and was really good at measuring the temperature of the surface. And you can actually see a model there based on real OTES and OVIRS data of the surface of the asteroid. And you can see where the heating is offset slightly to the afternoon side, just like it would be here in Arizona when it's really hot. Hottest point isn't noon, it's usually at 2 or 3. The Canadian Space Agency contributed the OSIRIS-REX laser altimeter, what we called OLA. And this was a point altimeter where we would fire a laser beam at the surface of the asteroid at rates as high as 10,000 hertz. So it's, many times a second there, 10,000 a second. And you would measure exactly how long it would take to come back. And so with those measurements, those high accuracy measurements, you can actually get a very good shape model of the surface. So you can get the actual distances, and we had a little mirror so you can raster around the surface somewhat. And we were able to build up maps of the surface with the OLA instrument, which is really cool. And then the final instrument was a student contribution. We opened up competition to universities all around the United States, asking for student groups to come up with an idea for an instrument. And the winner was this REXIS instrument, which was built by a team from MIT and Harvard. And it was looking at basically X-rays coming off the surface. Now, the surface of Bennu doesn't create its own X-rays, but when there's been major solar flares, you will actually have the surface of the asteroid fluoresce, and that will produce X-rays that would then get picked up by this instrument. And you would be able to differentiate between the various elements on the surface. And one of the cool results was, as they were scanning around the asteroid, and this is actually what you're seeing in this video is off the body, they kept picking up this bright X-ray source in space that wasn't related to the asteroid. And it turned out to be an X-ray outburst or flare from a black hole. So that was pretty cool. So why did we go to the asteroid Bennu? As I mentioned before, there's about 1 million asteroids out there. And just to show you how quickly things change, this pyramid diagram you see here on the left, that was produced, probably about 10 years ago, when we had 500,000 asteroids. And now we're at almost 1 million asteroids out there. So you would think with 1 million asteroids, you would have plenty of objects to go to. But most asteroids are out in the asteroid belt. And that would be a really long mission with taking a really large rocket to go out to the asteroid belt, rendezvous with the asteroid, collect sample from its surface, bring it back to Earth. So you want to limit yourself to asteroids that are closer to Earth. And that cuts that number from 500,000 to probably closer to 20,000 now, but it was 7,000 10 years ago, near-Earth asteroids. But even just because it's a near-Earth asteroid, which means it has an orbit that comes within at least 1.3 AU of the sun, 1.3 AU means 1.3 times the Earth-Sun distance. A lot of those objects either get too close to the sun, where you have thermal problems, get too far from the sun, where you have to worry now about how do you power your spacecraft. In highly inclined orbits, which means the tilt is inclined a lot with respect to the Earth's orbit. So again, you need a lot of energy to pump your spacecraft up to get to the high inclination. So if you limit yourself to those objects that require a minimum amount of energy for your rocket to get there, all of a sudden this number drops to about 200. And then the problem is most of these objects that have very Earth-like orbits are extremely small, which means they were only observed for hours to days when they were passing by the Earth. They are now since lost. Or if they're really small, they're extremely rapid rotators. The typical asteroid rotates no quicker than about 2 to 3 hours, but that's only true for objects 200 meters or larger. If you get under 200 meters, you can have asteroids rotating on the order of 10, 20 seconds. How do you land on something like that? And does something spinning that rapidly actually still have material, or has it thrown it off? So if you limit yourself to the larger objects that are easy to get to, now all of a sudden you're at about 24 asteroids. And at the time when we were doing this analysis, only 5 of those looked like they were carbonaceous, of which only 2 we had definitive proof they were carbonaceous, as in you had spectroscopy that really said this is a carbonaceous object. And those 2 objects ended up being Bennu, our target, and Ryugu, the Japanese target. Since then, there's been one other one discovered, a 2008 EV5, which the Europeans were considering going to with a mission that ultimately wasn't funded. And the reason why Bennu kind of rose to the top over Ryugu was because we had radar observations from Arecibo and NASA's Goldstone, our radio telescope. So we actually had we had high resolution imagery of the surface. And it suggested a surface that was very benign with lots of small pebbles and not a lot of boulders. So of the three small near-Earth asteroids that have been visited by spacecraft, Eros was actually much larger than these guys, and it was about 10 to 20 kilometers across. You can tell Ryugu and Bennu kind of look similar. They have a similar shape. Ryugu is the one on the left, the large one. Bennu's in the middle, and Itokawa, which is a different class of asteroid. It's not carbonaceous, but a stony asteroid. It's kind of more like a bent hot dog. But Ryugu and Bennu look similar in that they've kind of got this spinning top feature, which I'll explain a little more about later. And just to compare Bennu and Ryugu with all the other objects that have been flown by, and this doesn't even include Ceres and Vesta, which would both dwarf Letitia, which is the largest object shown here. Ryugu and Bennu are these little guys, these itty bitty rocks in there. And even Itokawa you can barely see. So these three are much smaller than the other objects like Matilda or even the comets that have been visited by spacecraft. So the OSIRIS-REX mission launched in 2016. We went around the sun once, and then in 2017 we had an Earth gravity assist where we passed relatively close to the Earth and used the Earth's gravity to boost us to that 6-degree inclination so we can match the orbit of Bennu. We arrived at Bennu late 2018. In fact, it was December 1st when the day we officially said we arrived, and we were no longer just approaching the asteroid, but we were starting to maneuver around the asteroid. And we spent most of 2019 either in orbit around the asteroid or maneuvering about it in such a way that we could observe the asteroid at different observing geometries, basically different phase angles. And that way we could get maps of the asteroid with the sun at noon versus 3 a.m. versus 3 p.m. versus 6 a.m. versus 6 p.m. as well as measuring the temperature of the asteroid. And then when we weren't doing the maneuvering, we were actually in orbit that either was about, say, 2 kilometers from the center of the asteroid or even as close as about 800 meters from the center of the asteroid. Remember, the asteroid's 500 meters across, so you're pretty close. You're only hundreds of meters from the asteroid when you're orbiting the asteroid. But it's a microgravity environment because the object's so small. So even when you're in that, say, 900 meter orbit, it still takes you 24 hours to orbit this asteroid, which just shows you just how slow all the motion was around asteroid Bennu. And then much of 2020 was spent doing what we called reconnaissance and rehearsals, where we started doing low flybys of various regions we were interested in sampling so we can get high resolution imaging and determine ultimately which sample site we would get. And then it was in October of last year that we actually collected our sample. So the mission started off with us slowly approaching Bennu, and this was the latter half of 2018 there. As you can see us zooming in, sometimes doing full rotation. And even from this relatively far distance here, you can tell that this object was pretty rocky, a lot of boulders on there. In fact, you can see a few boulders rotating in and out of view as they appear on the horizon there. And so the hope that we would actually show up at Bennu and find nice, almost like beach-like material, sandy playas or whatever that we can easily sample, turned out not to be the case. Most of the asteroid turned out to be covered in lots and lots of rocks. I mean, how do you collect the sample? How do you even get close to an asteroid and collect the sample when it's just boulders on top of boulders on top of boulders on top of boulders? So that was the first real surprise when we got there, that even though the radar imagery had suggested that the asteroid would not look like this, turned out it did. And the Japanese had a similar problem with Ryugu when they went there. The second big surprise of the mission occurred only a week after we entered orbit. So what happened was we just entered orbit. This was our 1.8 to 2 kilometer orbit. I was actually looking through the navigation data, and as I was flipping through the data, and this was those NavCams I was talking about before that weren't meant for science originally. They've got about a 30 by 40 degree field of view. They go down about 6th, 7th, 8th magnitude. So, from a dark sky, you start recognizing the star patterns because it's the same stars you see from a dark sky. So you sit in there and you see Lyra go by and Scorpius and Canis Major. And then all of a sudden noticed in one image, there was a huge star cluster. This is the asteroid here. It's a 5-second exposure, so the asteroid is saturated. But you saw this star cluster just sitting off the northern limb of the asteroid. And I didn't recognize that as any star cluster I knew about. I thought, well, maybe it's something in the southern hemisphere. But then when I looked up where we were pointed, well, we're pointed kind of in the Hydra region, so around the celestial equator. So it's like, nope, there's no big bright star cluster there. And as you start, stretching the contrast of the image, you start noticing these trails. And the further you get from the asteroid, the longer the trails are. And if you draw lines back, they all converge on a point on the surface. So what we ended up seeing here, this was January 6th of 2019, was some sort of ejection event. Something was throwing particles off the surface of the asteroid. And almost everything you see, especially in this region of the image, are particles. And there was about, I think we counted about 500-600 particles in this event. These particles were in sizes of millimeters to centimeters that were being blasted off the surface. Of course, the first thing we did on the mission was go, uh-oh, is this a threat to the spacecraft? We quickly had emergency meetings and decided, okay, let's do our risk analysis, figure out whether or not it's safe to stay in orbit around the asteroid, or do we have to back off and go away? We decided that it was safe to stay in orbit. That these particles were small enough and moving slow enough they wouldn't be a hazard to the spacecraft. And still, even being 2 kilometers away from the spacecraft, there's a lot of empty space out there. So what we did do was we started monitoring for these particles whenever we could, and quickly discovered that the asteroid is continuously throwing particles off the surface. And this video here shows a few of the events that we've seen. The largest event produced about 1,000 particles thrown off the surface, but we also had a lot of events that only threw off a single particle, which was really odd. Some of these particles were ejected at a fast enough velocity they completely escaped Bennu, so they're creating a very tenuous and weak but very real Bennu meteor shower. Some of the particles, and like you can see one right here, actually were in orbit and stayed in orbit for up to a week, making multiple orbits around the asteroid before they finally fell onto the surface. But a lot of the particles were just suborbital. They blasted off the surface and they landed somewhere else. So that made Bennu an active asteroid, which was really cool because one of the reasons why we selected Bennu in the first place, because it's technically a B-type asteroid, is that B-type asteroids seem to show cometary activity. Phaethon, which is the Geminid parent body, is a B-type asteroid. Wilson-Harrington, which is 107P down here, that was a comet for a few days. That's a B-type asteroid. 133P El Pizarro, which seems to show cometary activity every time. This is an object in the main belt. Shows cometary activity every time it goes around perihelion, is a B-type asteroid. So one of the reasons why we selected Bennu and even looked for activity in the first place was we thought, well, maybe it's an active asteroid. But what is an active asteroid? Now, active asteroids come in a whole bunch of different flavors. Objects like P2010A2 and Sheila, that's the result of an impact. Something came in and impacted the surface of that asteroid and created a giant debris cloud. And it kind of superficially looks like cometary activity. You get a coma and a tail, but really it's just, you're looking at a debris field. Other objects do seem like they have volatiles or ices either on their surface or just underneath their surface, and they show more traditional cometary activity. An object like Gault, and this is Hubble images of Gault, is a fast rotating asteroid that just seems like it spun up so quickly that it started having landslides. And those landslides ended up escaping out into space. So basically it's spinning so fast, the asteroid is starting to fall apart. And every time it spins up, it releases some material. And that again, superficially, it looks superficially like a comet tail. Or this comet Pan-STARRS down here, where the object spun up so quickly, it just completely disintegrated and fell apart. So some of these active asteroids don't really have anything to do with cometary activity. But based on the knowledge we have from Bennu and its particles, it looks like Bennu is not a traditional comet per se, that we're seeing activity because there's ices sublimating and knocking material off. It's looking more like either rocks are fracturing just because of thermal cycling. They get hot and cold as the asteroid rotates every 4 hours. Or the asteroid is just getting hit by micrometeoroid bombardment. Here on Earth, we're safe because the atmosphere protects us from most of the meteoroids that hit us. But on Bennu, there's no atmosphere. So you're constantly getting hit by even small particles coming in at, tens of kilometers a second. And that's enough energy to then kick off particles that are already free and liberated on the surface. Another thing that we weren't quite expecting was when we got to the asteroid. I mean, we knew the asteroid was dark. We knew it had an albedo of about 4%, which is pretty dark. 4% is about as dark as coal. It's in fact a few times darker than fresh blacktop. If you have your, see a paved road or have your driveway paved with blacktop, it's even darker than that. And what we found was there were kind of three families of boulders. There were really dark boulders, still dark, but not quite as dark boulders. And then we found some evidence of really bright boulders. And it's interesting because this is probably telling us a lot about the history of this object. For example, what we're finding is that there are, even though the asteroid in general is blue, there are what we call red units. There are parts of the asteroid that appear red. And we think this is due to space weathering. Just like if your car is parked out in the Arizona sun for years and years and years like mine, it's not quite the same color blue it was when it came off the lot. And it's because of, mostly it's because of sunlight that is now changing the color of the car or changing the color of your house. And that's space weathering, where you've got material that is baking in the sun, it's baking in that radiation environment, it's getting hit by micrometeoroids, and so it actually changes over time. So the thinking is that the freshest material is dark and red. Then as the material gets older, it turns blue, but it's still dark. So the blue, and then as it gets even older, it turns into light blue. So the transition from red to blue is a little bit faster than the transition from dark to not so dark. And so we think we can tell by looking at the albedo and the color of the surface, you can tell a little bit about the relative ages of all these various components. What was also interesting are these brighter objects. And these brighter objects not only are brighter than the dark boulders, but they also spectrally look very different. And here's some examples of these bright boulders. In fact, spectrally, these don't look like carbonaceous asteroid material. The boulders we're seeing on Bennu look like pieces of the asteroid Vesta. Remember, 4 Vesta is the brightest, one of the largest, and it is the brightest asteroid in the main belt because it's high albedo and it's also on the large side. Vesta is also basaltic. It has a lot of, it probably had a lot of volcanic activity back in its past, and it was the target of the Dawn mission. So how do you get pieces of Vesta on the surface of an asteroid like Bennu? And we'll talk about that in a few slides. Another nice find was evidence of what looks like these bright veins within boulders. And so spectrally, this looks like carbonate. And what's interesting about carbonate is that suggests that just like veins on Earth, where you have a silver vein, a gold vein, stuff like that, this suggests that this material was laid down by water, that you actually had active water moving around within the asteroid, and stuff was precipitating out of that water and creating these veins of bright material. So it does provide evidence that Bennu, or at least the object Bennu used to be a part of, had an active hydrothermal cycle. We also see evidence of that because the entire surface is what we call hydrated, which means it's covered in minerals that have water within its matrix. And so that suggests again that Bennu originally came from a water-rich body in its past. It is interesting that the Japanese mission, the Ryugu mission, actually does not have evidence of hydration. So for whatever reason, that asteroid seems to have been dehydrated. A lot of that water has been driven off. And that may actually tell us a little bit about its recent past. In order for Bennu to still have this sort of material on the surface, it could not have been heated to very high temperatures, which means it must not have gotten much closer to the sun than its current 0.9 AU. Ryugu, on the other hand, maybe in the past did get closer to the sun, and that's why its surface is more baked. Having this material on the surface where we can image it also suggests that the surface is fairly young in a geological time frame, and that it's only been exposed to the space environment for 1 million years, or probably even less. We also see evidence, in addition to the fact that we've got particles blasting off the surface every day, of a sort of a dynamic surface for Bennu. Obviously, there's there's signs of impact craters that are kind of muted on the surface, but we also see small signs of impact craters within boulders themselves, where a much smaller meteoroid hit the surface, hit the boulder, and then produced almost like, shooting a rock, like with a BB or something, and produced a little divot in the surface. We also see evidence of motion of material from the mid-latitudes and the high latitudes towards the equator. And that makes sense for an object that is kind of a rubble pile, but is also spinning very rapidly, that you'll see material moving from higher latitudes to lower latitudes, which could explain why Bennu has this equatorial bulge. A lot of this may be material that is moving down from mid to high latitudes and then collecting at the equator. And one nice thing about having the particles was that the particles acted like gravity test particles in orbit around the asteroid. By measuring their orbits and how they interacted with the asteroid itself, we could probe the gravity field and the internal structure of the asteroid. And that resulted in a nice study that said that the inner core is actually less dense than the outer core. Usually what most bodies, like, look at the Earth, look at the moon, you've got this dense inner core. For something like Bennu, it looked like material probably moved out from the inner section of the asteroid to the outer section because it was spinning so rapidly. And so you actually had a less dense inner core. And then the rest of the asteroid actually has a little more density, but then the equatorial bulge itself is less dense. So we're not exactly sure why this is, if this is a relic of when Bennu reformed after the initial collision that created all the debris that Bennu formed out of, or is this the result of Bennu spinning much more rapidly in the past? Right now, Bennu's orbital period is about 4.3 hours, but if it were spinning at around maybe 3.5, 3.6 hours, it would start falling apart. So it's not that far from spinning so rapidly that pieces would fall apart. So now that we have all of this information, and of course we'll know even more when the samples come back, what can this actually tell us about the history of Bennu? So Bennu wasn't always a 500-meter in diameter object. In fact, for most of the solar system, Bennu, or the components that now make up Bennu, were probably sitting inside a much, much larger parent body. Probably an asteroid that was 100 to 200 kilometers across, and it would have been a carbonaceous asteroid, most likely in the inner main belt. At some point, sometime between 0.7 and 1.6 billion years ago, that large, proto-Bennu parent was impacted by something that completely disrupted it. And as a result, both the parent body and the impactor were shattered. And it's very possible that those Vesta pieces that we're actually seeing on the surface, which may or may not actually be from Vesta, it just may be an asteroid that had a similar geological makeup composition as Vesta. But when that Vesta-like object hit Bennu, they both shattered, and now you had basically a debris cloud that was mostly dark carbonaceous material, but also had some of that bright impactor material scattered within it. And from this material, reaccumulated a bunch of asteroids, including Bennu. So Bennu actually reaccumulated from the debris cloud of this impact that occurred 0.7 to 1.6 billion years ago, we think. And we will actually get a good idea of the actual date when the sample comes back. We'll actually be able to use a radioisotope dating to figure out a lot of these kind of stressful events that happened in the history of Bennu. Like, when did this major impact occur? And it's also possible that Bennu, again, didn't just form out of, there might have been a larger Bennu that formed, and then it got shattered, and another Bennu got formed, and it got shattered. So there could be many different cascading, almost life cycles of big object gets broken up, smaller objects form, they get shattered, even smaller form, they get shattered, and then we have Bennu itself. And then sometime 10, 20 million years ago, your Yarkovsky effect, which is back when I showed before, as the asteroid was rotating in the thermal, you can see that the heat was primarily on the afternoon as well as the evening side. Radiating that heat produces a thrust, which actually moves the asteroid. And so eventually the asteroid, which formed out here in the middle of the inner main belt, moved to the inner edge, fell into what was called the Nu 6 resonance, which is why the main belt kind of has an inner edge, and got perturbed into a near-Earth asteroid orbit, and has spent the last couple of million years now in the inner solar system, or currently orbiting between the orbits of Venus and Mars, though that probably changed at times. But we'll also be able to tell from the samples how long that material has been on the surface, which also can tell us a little bit about how long the asteroid has actually been in the inner solar system. So we'll learn a lot about the past history of objects like Bennu when the samples come back. But now for the really exciting stuff, the actual sample collection event. So originally we had selected, I think it was like 16 sample sites, and then we kind of chopped it down to 8, and then chopped it down to 4, and then eventually we ended up with Nightingale, which was our primary sample site, and a backup sample site in case Nightingale didn't work. And when we first designed the mission, we were hoping to sample a site, have an uncertainty of about 50 meters or so, thinking there would be a nice big flat spot on the surface with no boulders, and it didn't matter we were off by 10, 20, 30 meters in any direction, it would be safe. But as you can see, when you stick that 50-meter circle, 50 meter in diameter circle on our Nightingale sample site, there are a lot of hazards that you do not want to run into. So we quickly had to find out, okay, how can we have the spacecraft land with an uncertainty that fits within an 8-meter site? As you can see, that's only 4 car parking spots across. This is not a large area. And remember, the spacecraft is about 20 light minutes away. So it takes 20 minutes for the spacecraft to send back to Earth what's going on, for you to respond with a command. So you can't joystick this down to the surface. So what we ended up doing was coming up with something called natural feature tracking, where the spacecraft wasn't smart enough to say, okay, I'm off target, so I'm going to, thrust in this direction to remain on target. But it was smart enough to say, am I still going to land on a part of the asteroid that's safe to land on? You can almost think of it as throwing a dart at a dartboard. You want to hit the bullseye. The dart's not smart enough to hit the bullseye by itself necessarily, but it is smart enough to say, hey, I'm still on target to hit the bullseye, continue going forward, or I'm way off, I'm going to miss the board completely. So let's just abort, fire the thrusters, go back to a safe distance, and we'll try this again next time. And that's exactly what happened. We did the first try. We could have done this 3 times. We had canisters to do this 3 times, but we went down to the surface and hit our target to within a meter, which was pretty amazing. Now, how do we actually collect material from the surface of an object that's microgravity? You can't really have any moving parts. You can't sit there with drills because, well, again, there's nothing holding you down. If you drill, the spacecraft would spin the other way. So what happened is we dropped down to a pretty safe distance of about 30 meters. We matched the rotation of the asteroid, and then we went into free fall. Now, again, it's microgravity, so you're only accelerating to centimeters per second when you finally hit the surface. We had this sample return capsule. I've also got it here. That came down and hit the surface. Now, if this sample return capsule looks, especially for us who are, 40, 50 years old or older, it looks like an old car air filter, the kind of thing you dropped into, your old Fords and stuff back in the day. That's exactly what this mechanism was based on. You dropped it onto the surface. As you can see, there are inert nitrogen gas canisters that would blow. The nitrogen would blow into the surface, would mobilize the asteroid material, the regolith, would be kicked up, and it would be caught by the air filter. So the air filter had a mesh that would allow the gas to escape, but the rocks wouldn't. And so it would collect the material there. And the plan was to collect up to 60 grams, though we knew under the perfect conditions, we could possibly collect up to 2 kilograms of material. So right now I'm showing a movie where this was taken with the TAGCAMS. So this is a 30 by 40 degree across field of view, just showing everything leading up to the TAG event as we're flying. And you'll see some bright, every once in a while, you'll see a bright boulder. Those are those vestoid boulders I was talking about. And then we descend down onto the surface. Here's Nightingale that we're approaching. And eventually you'll see the shadow of the tag head come into view. There it is. Hit the surface, boom. We spent about anywhere from 5 to 10 seconds on the surface. And that includes after the gas actually erupted. And then material was thrown all over. And here I'll cut out the lead in so we can just watch this video of the kind of the chaos we created. And again, you can see some really bright stuff. You see the material on the coming in from the bottom is actually the surface of the asteroid, while a lot of the stuff you're seeing at the top isn't the surface, it's that cloud that was kicked up not only by the actual sample event itself, but also by the thrusters then firing as we moved back away from the asteroid, and those thrusters actually kicked up and redirected a lot of this material as well. And then this is from the SAM-CAM, which is looking directly at the head, the sample head. As it hits the surface, the gas fires, and then we back off. So it was funny when we actually were designing the mission. One of the things we were worried about was, how would we know we actually collected any sample? And how would we know we actually collected enough sample? So one of the things we planned on doing was, even before we had any sample, we kind of just did a moment of inertia test. And then we would do it again with sample in the arm. And then we would see, okay, can we actually figure out exactly how much sample we now have in the arm? And even before that, we were going to do an observation where we took a picture directly into the sample head to see was there any material there. And so the last big surprise of the mission, at least until the sample comes back, was not only did we have sample, we had almost too much sample. Every time we were moving the sample arm in order to take a picture of it, material was coming out of the sample head. And it's great because if you look closely, like for example, this piece here, a lot of these things are flakes. And that made me and a lot of other people feel really good, because one of the things we learned from studying those particles, where we combined the photometry we had gotten from the particles with the orbital dynamics we derived from those particles being in orbit around the asteroid, was that they were probably flakes. And so here we had confirmation already, even before the sample had come back to Earth, that we have flaky particles, which was great. Now, why were we shedding particles? Well, if we go back to this image here, you'll see that there's this mylar flap. Oops. There's this red mylar flap here that opens, and then it should close when the collection event is done. Well, we collected so much sample that the flaps were jammed open with material. And so, as it turns out, not only did we collect sample, we collected probably a lot of sample. We don't know exactly how much, but definitely more than the 60 grams that we were planning on collecting in the first place. Just to show, as we kind of stowed, and if you look closely, you will see a few particles escaping and coming out when we finally stowed the sample head here in the sample canister. And this is the part of the spacecraft that will actually return to Earth. And just about a week or two ago, the OSIRIS-REX spacecraft did one last flyby. Originally, we weren't planning to do this, but the decision was made, let's do one last flyby about 7-8 kilometers from the asteroid surface and just look at what happened. And you can see that we uncovered a bunch of material, and in the case of this rock, through this rock, quite a large distance, about 40 feet or 12 meters. this object was thrown. But in general, once you get about 10, 20, 30 meters from the sample site area, doesn't look like a lot has actually changed. So now that OSIRIS-REX has conducted its last flyby, it's actually about to head back home. In fact, the May 10th, which is about 2 weeks from now, the thrusters will fire and Bennu will start on its return journey, which is about 28 months. And it will eventually come back and drop its sample off on Earth on September 24th, 2023. Spacecraft and the instruments are still in great shape. We can't collect any more sample because we won't have that sample head anymore, because that's going to return to Earth with the sample. But the spacecraft can go on to observe, either flyby or rendezvous with other asteroids to study them up close. And so that's something that the team is looking into. But OSIRIS-REX isn't the only asteroid mission out there in the future. NASA has a bunch of missions, as well as the Chinese and Japanese space agencies. The next two Discovery class missions, Psyche and Lucy, are going to launch in the next year or two. Psyche is kind of like Dawn. It will go into the main belt and orbit a large asteroid, but it's going to orbit 16 Psyche, which we believe is almost all iron nickel. So it represents the remnant of the inner core of a much larger body that has since broken up. Lucy will fly by one small main belt asteroid and then numerous Jupiter Trojans, which are objects that are in a one-to-one resonance with Jupiter. So they kind of share Jupiter's orbit, but they are, 30 to 90 degrees from Jupiter on either side. And these objects are carbonaceous, could be related to comets, and may very well have been trapped in those orbits for the history of the solar system. So this is yet another mission that's going to material that will tell us a lot about that early history of the solar system. Another mission that's launching this year, actually, or maybe it's been postponed to next year, is the DART mission, which is the double asteroid redirection test. And this is a NASA European mission to actually impact the secondary of a binary asteroid. So it's a binary asteroid with a satellite. We're going to hit that satellite and actually see how impacting that satellite changes its orbit, so you can learn a lot about the internal structure of the asteroid and actually teach you quite a bit about how you could deflect asteroids in case you have one on a collision course. Janus is a small sat that will fly by two binary near-Earth asteroids, also study binary near-Earth asteroid dynamics and mechanisms. The Chinese have a mission scheduled in 2024, which will go by, it used to be 2016 HO3, Kamualua, which is actually a Earth Trojan asteroid that is in it's in a one-to-one resonance with the Earth. And as well, it will fly on to one of these, it will fly on to 311P Pan-STARRS, which is an object that actually broke up. So it'll be going to an asteroid that looks like it's actually shed material recently. So it'll be kind of cool to see an asteroid that is actively, and maybe even we'll do it when the Chinese mission is there, shed material from the surface because it's rotating too quickly. And then the Japanese have a sample return mission to Phobos. Phobos may or may not be a captured asteroid. It's also very possible Phobos is the result of debris from an impact on Mars that then coalesced back into a satellite. They have a flyby mission called Destiny Plus that will fly by the Geminid parent body, 3200 Phaethon. And the Hayabusa 2 mission is not done. Even though it's dropped off its Ryugu material, it's going to fly by another near-Earth asteroid in 2026 and then rendezvous with a very small asteroid called 1998 KY26 in 2031. And by very small, I mean it's like 30 meters across. And it's rotating once every 10 minutes or so. So KY26 is the same size as the large boulders on Bennu, which is pretty interesting, pretty cool. And then finally, in addition to having worked on the OSIRIS-REX mission and now working on my own company, working to develop software for future missions, of course, I'm also involved in a lot of amateur astronomy groups like the Association of Lunar Planetary Observers, where I'm the Comet section coordinator. But with Dolores Hill, who's also ex-OSIRIS-REX, we are the coordinators of the Target NEO's observing program at the Astronomical League. This is a program where we try to encourage observers to use their, modest, and when I mean modest compared to a 1, 2, 3, 10-meter telescope, modest backyard facilities to observe near-Earth asteroids, even asteroids that are relatively faint, 17th, 18th, 19th magnitude, to learn as much as possible with, telescopes as small as 6 to 12 inches in diameter. And what we're really looking forward for is not just astrometry measuring the position of these objects, but also, taking lots of exposures and co-adding them to figure out the phase function of an object, which tells you something about the albedo of an asteroid. Do light curves, derive colors. What can you learn with an 8-inch telescope of these objects to actually tell you something about their sizes, their shapes, their colors, their taxonomies. And with the use of programs that some are free and some are paid, but they're not very expensive, but programs like Astrometrica, Canopus, and even Tycho Tracker, they almost act as force multipliers, especially in the case of Tycho Tracker, where you can have a small telescope, take lots of short exposures and co-add them, and it will look for objects that are moving at different rates. And you can actually discover objects that are almost as faint as what the surveys are doing now, as well as doing light curve work and such. So if you're looking for an interesting observing program, your next observing program at the AL, look into target asteroids. And that is the end of my talk. Hope you all enjoyed it.
Well, thank you, Carl. I have a few questions for you about this. One of them, it just came to mind, and probably something that you guys all jumped on when you saw that the stuff flowing out of the collection sample looked like flakes. Did you think about static electricity? How that's going to affect a very fine flake-like objects? Because on Earth, you'd have stuff all over because of static electricity.
Yeah, in fact, static electricity was one of the things that we were going to look for when we actually got there. Not that we could actually detect the electrical charge itself, but we actually had people on our science team who specialize in that, who were theorizing that electrostatic levitation could actually remove small particles from the surface of an asteroid.
Well, I'm thinking that looking at that picture, what are the diameters of these flakes are less than a millimeter, I would think. Is that true?
Millimeters or centimeters here.
Okay.
Yeah. Some of the largest are probably on the order of a centimeter.
Yeah.
And that's actually something that maybe, I'm not sure if the team is looking into this. The spacecraft itself is kind of charged up, so it might have a little bit of an electrostatic field around it. And so as these particles are moving away, can you actually see sort of deflections? Mm-hmm. That's something we thought maybe we saw when the spacecraft, even before we got the asteroid, the spacecraft was shedding particles, which probably was just water that was trapped within the folds of the kind of our reflective thermal blankets. And as we were moving the spacecraft, that ice was seeing the sun for the first time, and you were getting sublimation, you have particles being released. There were a few curved particles, which makes you wonder if it weren't curving along kind of field lines of something.
Yeah. And another question is, so these particles are all captured in the sample container, and good fortune has it that the spacecraft makes it back to Earth, and you open it up. What do you hope to find? What are you looking for? What are these all these particles, the greater than 60 grams, maybe up to 2 kilograms or something, sample you have? What's that going to tell you? What are you looking for? Composition, shape?
Yeah, all those things. One thing we're really hoping for, now that we know that there's bright material, is there pieces of VESTA? Did we actually end up inadvertently becoming the first VESTA sample return mission as well? We're hoping that there's, gases. I'm not sure we'll necessarily find ices, but hopefully we'll find some sort of water molecules trapped within the matrix, mineral matrices. And, organics. Here's material that, we know we've got meteorites that are similar to what we think Bennu is, that had amino acids, within them.
Well, when the sample return enters Earth's atmosphere and lands, I will assume that the samples are secured away and they won't have any contamination from Earth's atmosphere and stuff.
Right. That's the plan. The sample will land in Utah. There's the UTTR test range up just to the west of Salt Lake City area. And then once we, have the sample on the ground, it'll immediately go to Johnson Space Flight Center. Well, they'll do their curation. But if everything occurs as planned, yeah, it's in a hermetically sealed sample return capsule. So there shouldn't be any contamination from the Earth environment, hopefully.
Yeah, well, I've been thinking not just contamination, but a reaction with Earth's atmosphere, with the oxygen in Earth's atmosphere could change some of the characteristics of these
Oh, it
particles.
definitely could. And that's also what I mean. No contamination from the atmosphere as well. Not just water and soil, but also the atmosphere.
Mhm. Well, that's, I have my fingers crossed. You've got it, what, September 24th, 2020,
Yep.
2.5 years.
And originally we planned on doing the sample collection. I think it was going to be September 2019. And then the decision was made. Then that got pushed back a few months. And we decided to wait until at least July 2020. That ultimately became October 2020. Because we wanted to do the sample collection when the asteroid was at aphelion, at its furthest distance from the sun. And the reason for that is because we knew that the sample was going to be sitting in this sample head for, days, maybe a week before we actually stowed it.
Mhm.
And if we were too close to the sun, we didn't want the sample getting so hot that it was actually driving off the really volatile material.
Mhm.
So we wanted to minimize that as much as possible. As it turned out with the Hayabusa 2 mission, Ryugu, when they came back, they actually did have gases in there.
Mhm.
So they were able to collect some volatiles that probably, escaped out of the sample, and we're hoping to have the same.
Well, the one video you showed, which I thought was quite remarkable, was of the particles being ejected from the asteroid. The ones that you thought at first was a star cluster, but no, it's particles being ejected. And I don't think this was a chance thing. This must be happening all the time.
Oh, yeah. I mean, the fact that the first event occurred only a week after we dropped into orbit. And then, yeah, I mean, we spent entire weeks where we were dedicated to just looking for these particle events.
Mhm.
And on average, there's at least one particle a day coming off the surface. And I'm sure there's a lot more that we didn't see.
And what were the reasons that you think that are causing this ejection?
So
Micrometer?
there's a lot of different ways to create these kind of active asteroids. One could just be your traditional, you've got ices, they're sublimating, you have jets coming off the surface carrying dust, just like a comet. So that's kind of traditional cometary activity. Then there's impacts, of which we think that's part of what's going on, where we've got impacts of micrometeoroids hitting the surface. Thermal fracturing, we know the rocks are breaking up into smaller and smaller pieces just due to basically thermal cycling. Just like in your backyard over times, rocks will break because of thermal cycling, because of heating and cooling, though we also have the added benefit of water and ice and all those things. And right now we're kind of leaning towards, well, the rocks are fracturing, and that's creating these little flake-like pebbles that now coat the surface. And then it's a meteoroid impact that then kicks that stuff off and ejects it almost like tiddlywinks, ejects it off into space.
Right.
But there's other stuff like electrostatic levitation, something you had mentioned before, where the particles, if they're small enough and there's enough charge, can actually come off the surface. And by themselves, they should fall back down. But if there's any other force acting on them, they can actually end up just leaving and escaping. And that may explain why we don't see really, really fine material on the surface of these asteroids, because they get removed by this electrostatic levitation quicker than they can form. There's solar wind sweeping. We think we see this with the Geminid parent body Phaethon, which gets extremely close to the sun, about 0.15 AU. And the solar wind is actually forceful enough, especially when you have a coronal mass ejection, to actually knock material off the surface. So you actually have, it literally is just like the solar wind is blowing on the asteroid and blowing material off.
Mhm.
And then there's rotational disruption, of which these images show, where the object spins up so quickly. And most of these asteroids are what we call strengthless rubble piles. They're aggregates of material that's only being held together by gravity. So if you spin too quickly, eventually your rotation velocity is so much at the equator that it escapes the gravity of, you basically, you get to escape velocity and you leave the surface and you throw material off.
It wouldn't
Either
take
here,
much.
yeah, it wouldn't take much. Either here, where you've got a large object throwing material off in discrete events, or here where it looks like it just completely came undone.
Mhm. Wow. Okay. Okay. You also mentioned that what you believe a little bit of the distant history of Bennu was that it may have been shattered multiple times,
Yeah.
its parent body, and then it itself has been maybe shattered and then coalesced again and then shattered again. So does this mean that it can be shattered again, yet again?
Yeah, definitely. Though you do wonder if it's of a small enough piece that even if you shattered it, would there be enough gravity among those small pieces to rebuild something back together? But it's possible. Yeah. And yeah, definitely Bennu can be hit by something. It doesn't have to be anything as large as Bennu, but it can be, you know, 10th the size or whatever. You can hit it and shatter it yet again.
Oh,
Though being now in the near-Earth asteroid population among the inner planets, there's a lot less material that can run into you or you can run into.
right.
Out here in the main belt, there's a lot of stuff. So there's probably a lot of these shattering events occurring.
Well, since it's so close to the Earth as it is, if it was shattered, we might have a pretty good meteor shower at some point.
Yeah. And the fact that, you know, these asteroids and these sort of active events are probably occurring on every asteroid. It's being hit by micrometeoroids. And as long as there's fine material on the surface, they're being thrown off. So does that mean every near-Earth asteroid has a, you know, meteor shower associated with it? It's not something that's obvious because we're not detecting a lot of them, but maybe something, you know, like Apophis, which is going to make a very close approach in 2029, will have an associated meteor shower based on, you know, a similar mechanism to Bennu where particles are constantly being knocked off it.
Well, I noticed near the beginning of your talk, you were showing pictures of these asteroids, Bennu, and there was a Japanese one. I don't remember what the name of it, but it looked just like Bennu.
Yes.
And okay, so you got these two asteroids that resemble each other fairly closely. So
Yeah.
that you know that little bloated shape it has with lots of little boulders on it. That must be I'm thinking that must be a pretty common scenario for asteroids of that size.
It is. And the thinking is that yeah, when an asteroid kind of spins up, you might actually shed material. Like, for example, Itokawa. If you took Itokawa and you spun it up rapidly, what would happen? It would probably split in two.
Mhm.
In each of those resulting pieces, you know, one end would be here, one end would be here. Each of those resulting pieces would probably end up with this shape.
Hmm.
A lot of material would escape, but then it would be spinning so rapidly, it would kind of conform to this sort of spinning top shape that we have there.
Uh,
So this is definitely a very common shape among asteroids.
uh, that's incredible.
And the other, you know, I mentioned that, you know, Bennu and Ryugu, and then there's this other one, 2008 EV5, are kind of the three best carbonaceous spacecraft targets on in the easiest to get to list. It looks exactly like Bennu and Ryugu. It's got also that spinning top shape, just based on the radar observations.
Well, I think we're all going to be waiting for September 24th, 2023.
Oh yeah, definitely.
And the weeks after when some of these studies get underway to figure out exactly what it is that you brought back. That is fascinating. I'd like to conclude here. And thank you, Carl, for mentioning about the Astronomical League
Mhm.
Near-Earth Object Target NEO program, because you're right. That is something in which amateurs can jump into and
Yep.
possibly even have a meaningful contribution. You know, you start on the program, you learn how to do this, you understand what's going on. You just might come up with something pretty cool.
Yeah, and a lot of amateurs have been making major contributions to asteroid science for years.
Mhm. Mhm.
While discovery is mostly done by professionals, there are still amateurs out there, especially if you use programs like Tycho Tracker, who are making discoveries even now of near-Earth asteroids and main belt asteroids. A lot of follow-up work after an asteroid gets discovered, especially near-Earth asteroids, because when they're first discovered, you don't know exactly what their orbit is. So the Minor Planet Center puts them on the Near-Earth Object Confirmation page. A lot of that follow-up work is being conducted by amateurs. And then if you go to like this paper here was published in the Minor Planet Bulletin, which is actually the Minor Planet section of the ALPO publishes this.
Mhm.
And there's probably about 24 papers every quarter that come out, and it's almost all amateurs.
Mhm.
or, you know, small colleges with relatively modest, and I mean, you know, they might still be half meter or quarter meter, but still not super large telescopes, doing light curve and color and photometry work of main belt asteroids, detecting binary asteroids, and as well as doing a lot of near-Earth asteroid work. So if you just go to the Minor Planet Bulletin, I mean, you'll find a lot of stuff where people are just using C11s and C14s and doing great work.
Well, that shows you that you can
asteroid research.
do this and have an impact on it. I shouldn't use impact, but have a meaningful contribution. So as you have it on your screen there, to do this, you just go to the Astronomical League website, go to its NEO Observing Program page, and that'll give you all the details. And that's a good way. Well, that's your first step in getting started on this. And I encourage people to do that if this tickles your fancy. So, well, Carl, I want to thank you again for doing this today, taking your time, and our audience out there, which will be through YouTube, and we will also post this on the Facebook page of the Astronomical League, so people can look at it in their leisure. But I think that they're going to come away wanting to know more about this whole subject. And it's not going to go away because, as I just said several times, September 24th, 2023, you'll be hearing about it whether you want to or not.
Oh, yeah.
So that's pretty cool. But anyway, I want to sign off and thank you all for joining. And thank you, Carl, again for your time and a great program.
Thanks, everyone, for listening, and I'll see you next time.
Adios.
Bye-bye.